Hello and welcome to this lesson for OCR A-Level Physics in Module 6, Particles and Medical Physics, in the topic of electrical fields, looking at the concept of electrical field diagrams. So, if we've been successful and we've learnt in today's lesson, we should be able to define what an electrical field is and link this to electrical charge, describe the different electrical fields and model a uniformly charged sphere as a point charge at its centre, and then finally detail the properties of electrical field diagrams. So in this lesson we're going to be looking at the following parts of the OCR A-Level Physics specification, 6.2.1, point and spherical charges. So a field is an important concept to define. A field is a region in the universe where an object placed inside of it can experience a non-contact force due to its position in the field. Now the properties of the field are given by the virtual particles of the force interaction. Now objects must contain a certain property to experience a non-contact force inside the field. In electrical fields, this property is charge. If an object has no charge, it experiences no force inside of an electrical field. Now previously we have considered gravitational fields, which act on objects with mass, extend to infinity, exert weak forces, and are always attractive. Now as we move through this topic, we will contrast electrical fields with gravitational fields, where electrical fields act on objects with charge, they do extend to infinity, they exert strong forces, and they can be attractive or repulsive. Now please remember all forces between objects are either contact forces, forces produced when objects are physically touching. So examples of contact forces include friction, air resistance, tension and the normal force. And non-contact forces, forces produced when objects can be physically separated. Examples of non-contact forces include the gravitational force, the electrostatic force and the magnetic force. Now objects can exert non-contact forces by transmitting a field in space. So as we said, a field is a region of space where a body can experience a force. So for example, an electron's electric field is a region of space where a charged object can experience the electron's electrical force, and these are represented by field lines. Now a source is always required to produce a field. Now for an electrical field, this is an object with charge. Now if other charges enter the field, then they will experience an electric force, attracting or repelling them from the object. Now since force is a vector, the direction of this force depends on whether the charges are the same or opposite. Now opposite charges, so positive and negative charges, attract each other, and like charges, so positive and positive, or negative and negative, repel each other. Now we visualize the effect of an electrical field with field lines. These are drawn as lines from the object with arrows on them showing their direction. So this is an example of a radial field produced by a uniformly charged sphere. So the field lines are therefore straight and are produced at right angles to the surface. Now here the electron has a negative charge, so will produce an electrical field. Now any charged object inside the electrical field of the particle will feel the electric force. The objects do not have to be touching. Now different electrically charged objects can have an interacting electrical field lines, but they cannot overlap. Field lines from charged objects can join up, but they cannot cross. Now the direction of electrical field lines and the density of the electrical field lines are very important indicators of electrical properties. Electrical field lines show the movement of a unit positive charge in the field if it was placed at this point. So electrical field lines always show a path a unit positively charged particle would take if placed at that point. So here, our positively charged particle would move towards the negative electron. So electrical field notations always consider the impact to a unit positive charge. Now there's no fundamental principle behind this rule. A positive charge is used to standardize all equations regardless of the context. So this means electrical field lines always show the path a positively charged particle would take if it was placed at this point. So for negatively charged objects, the field lines point towards the particle. In this instance, our proton has a positive charge, so it will produce an electrical field. Now this positively charged particle would move away from the positively charged proton. Now as we said, electrical field lines always show the path a positively charged particle would take if placed at this point. So for positively charged objects, the field lines point away from the particle. Now how close the electrical field lines are together, the density of the field lines shows how strong the electrical force is. The denser the field lines, the stronger the force exerted. Now here, the field lines are close together, so the force produced is strong. Whilst here, the field lines are more spread out, so there is a weaker force produced. So to clarify, an electrical field is a region around a charged particle within which a non-contact force will be exerted on other charged particles. All charged objects produce electrical fields. Electrical fields can be represented by field lines. Electrical field lines show the path a unit positive object on the line would take. The density of the electrical field line shows the strength of the electrostatic force. All field lines should meet and intersect at the centre of mass or the centre of charge of the object. So for a symmetrical object, they are in the same place. Electrical field lines show the path a positive object on the line would take, and the density of the electrical field line shows the strength of the electrostatic force. If the electrical field lines meet at the centre of the object, we call this a point charge. Now in this diagram, the electrical field lines do not meet as this is a charged object, so are drawn from the surface as you do not know the electrical field inside the object. Now for a point outside a spherical conductor, the charge of the sphere may be thought of as a point charge at its centre. So a uniform spherical conductor is one where its charge is distributed evenly. So we can say the electrical field lines around a spherical conductor are therefore identical to those around a point charge. So an example of a spherical conductor is a charged sphere. Now, as we said, the electrical field lines would show the path a positive object would take, and the density of the field lines show the strength of the electrostatic force. Now, you must be able to draw electrical field lines accurately and not make mistakes in these diagrams. So we can summarise the electrical fields around a spherical conductor as follows. Now, the interaction of field lines and electrical field lines can produce many complex patterns, such as the following. So here are two like charges. This produces a repulsive interaction, and this is shown as the field lines move away from each other. It also produces an area between the objects where the force is zero. There are no field lines in this area. Now the field lines are directed from two positive or negative charges, and therefore as well we can say the closer the charges are brought together, the stronger the repulsive electrical force between them becomes. Here, there are two opposite charges, so this produces an attractive interaction. This is shown as the field lines join together. This produces an area between the objects where the force is higher, as there's a greater density of field lines. Now the field lines are directed from the positive charge to the negative charge. Now the closer the charges are brought together, the stronger the attractive force between them becomes. Now we can see this in this diagram as shown. Now remember, the direction of the field lines show the path a positive test charge would take if it was placed there and is not acted upon by another force. Now it's better to show electrical field lines as an animation, as it shows the path taken by a uniform point positive charge in the electrical field, as shown in the following diagrams. Now you need to be able to show the motion of charged particles in an electrical field with the field line shown. Now charged objects can produce two electrical fields of two different types. We've got a radial field and we've got a uniform field. Now the radial field is produced by any particle, point charge or uniformly charged sphere, whilst the uniform field is produced by parallel metal plates such as a capacitor. Now in both instances the electrical field lines point in the direction a positive charge would take, but for the radial field the electrical field strength decreases with distance in the field, whilst for the uniform field the electrical field strength is constant throughout the field. But as we said before, in both instances the field lines indicate the movement of a positive charge placed in the field. Now when a potential difference is applied between two parallel plates, they become charged. Now you can see two things in this diagram. Firstly, the electrical field between the plates is uniform, but the electrical field beyond the edge of the plates is non-uniform, and they're shown by which have been shown by the circular red lines. Now the field around a point charge travelling between two parallel plates combines the radial field of the point charge and the uniform field between the two parallel plates. So the electrical field lines between a point charge and a parallel plate are like a field line between two opposite charges, and the field lines become parallel when they touch the plate. So to summarise what we've looked at in today's lesson, electrical fields are due to charges. Modelling a uniformly charged sphere as a point charge at its centre, and electrical field lines can be used to map electrical fields. So if we've been successful and we've learnt in today's lesson, we can define what an electrical field is and link this to electrical charge. Describe the different electrical fields and model a uniformly charged sphere at its point charge at its centre. and then finally detail the properties of an electrical field line diagram. So, thank you for watching this lesson, which is part of Module 6, Particles and Medical Physics for OCR A-Level Physics, in the topic of electrical fields and the concept of electrical field diagrams. Thank you so much and have a lovely day. Hello and welcome to this lesson for OCR A-Level Physics, Module 6, Particles and Medical Physics, in the topic of electrical fields, looking at the concept of Coulomb's law. So if we've been successful and we've learnt in today's lesson, we should be able to define what the force experienced on charged objects when near other charged objects are, note the similarities and differences between the gravitational field of a point mass and the electrical field of a point charge, and then calculate and describe the electrical force experienced on charged objects in an electrical field. So we're going to be looking at the following parts of the OCR A-Level Physics specification, 6.2.2 Coulomb's law. Now, our understanding of electric fields took a long time to develop. Now, both gravitational fields and electrical fields follow the inverse square law when considering the force produced between the two objects. Now, this occurs as both gravitational fields and electrical fields work by the same underlying mechanism. We consider mass producing a gravitational field as a point mass, and the charges producing an electrical field as a point charge. Now, both field lines spread out as spheres, and this gives a 1 over r squared relationship due to the surface area formula of a sphere. So if we consider a point charge producing an electrical field, we can say that the greater the distance from the electrical charge, the larger the spherical electrical field. Now, this area is given by the equation 4 pi r squared, and this gives our inverse square relation. However, there are two major differences between gravitational fields and electric fields. Firstly, the field strength of each field, which is represented by different constants in the equation. And secondly, the electric field can be attractive or repulsive, represented by a positive or negative value, whilst the gravitational field can only be attractive. Now, in 1785, the French physicist Charles-Augustin de Coulomb published his first three reports of electricity and magnetism, where he stated the mathematical relationship between the electric force and the distance between objects. Now, he used a torsion balance to study the repulsion and attraction forces of charged particles and determined that the magnitude of the electrical force between two point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them, and he called this Coulomb's law. So Coulomb measured the electrostatic force between two electric charges. He defined opposite charges given an attractive force as given a negative value for the electrostatic force. This occurs as a positive times by a negative is equal to a negative. Also note, we also measure r, the separation of the charges, to be from one centre of mass to the other centre of mass. Now, Coulomb defined same charges which provide a repulsive force to give a positive value for the electrostatic force. This occurs as positive times by positive is a positive, and a negative times by a negative is equal to a positive. So Coulomb measured the electrostatic force between two charges, and he deduced that the magnitude of the force F between charges Q1 and Q2 is proportional to the product of Q1 and Q2, i.e. Q1 times Q2, but inversely proportional to the square of this distance r between them, and this forms the basis of Coulomb's law. So this means that our relationship between force and separation is F is equal to 1 over r squared. So this tells us that when the separation is doubled, the force exerted decreases by a factor of 4, 2 squared. Now, you must be able to state the relationships of Coulomb's law as well as state the mathematical equation. Now, so as we know, F is proportional to Q1, Q2 over r squared. Then Coulomb then deduced the constant of proportionality between the factors. Now, we can therefore say that our constant of proportionality is k, where k is equal to 1 over 4 pi epsilon 0, where epsilon 0 is the permittivity of free space, which is 8.85 times 10 to the minus 12 farads per meter. Now, this value can change depending on the material between the charged objects. At A level, it's assumed that there's air or vacuum between the objects. If there was a different medium between the charged objects, there would need to be a different constant used in the calculation. So therefore we can now state Coulomb's law as F is equal to 1 over 4 pi epsilon 0 times by Q1 Q2 over R squared, or F is equal to Q1 Q2 over 4 pi epsilon 0 R squared. Now this equation calculates the electrostatic force between two objects due to their electric fields. It also will indicate that both charged objects will experience this force. So this force is the same force on each charge. Now each charged object may accelerate a different amount if they have different masses. As we know, acceleration is equal to the resultant force over the mass. Now, our Coulomb's law is very similar to Newton's law of gravitation. However, charge is used instead of mass, as charge produces the electrical field. In addition, a much larger constant is used in the equation, as the electric force is much larger than the gravitational force. However, it must be noted that Newton's law of gravitation and Coulomb's law are very, very similar. Now for Coulomb's law to be accurate, there three assumptions have to be made. Assumption 1. Objects are considered as point charges. The charged objects must not be touching, and they must also be stationary. So here is a summary of Coulomb's law. So let's now have a look at an example calculation using Coulomb's law. Find the force experienced by a free electron 2.83 mm from the centre of a 1 mm sphere carrying a charge of plus 0.510 microcoulombs. The charge of an electron is minus 1.60 times 10 to the minus 19 coulombs, and the mass of an electron is 9.11 times 10 to the minus 31 kilograms. So we firstly identify the force given between the two objects is calculated with Coulomb's law. F is equal to 1 over 4 pi epsilon 0 times by Q1 Q2 over R squared. We then identify our two charges and the separation between the two charges from the question. Now remember, the separation from the centres of masses is what is going to be our value of R, okay, not the surfaces of the object. So we then place these values into the Coulomb's law equation to say 1 over 4 pi epsilon 0 times by 0.51 times 10 to the minus 6 times by minus 1.60 times 10 to the minus 19 over 2.83 times 10 to the minus 3 all squared. Now, when you then calculate your force exerted, remember F is equal to minus 9.16 times 10 to the minus 11 newtons. Now please remember, in this question the R term is squared. People commonly forget to do this. Finally, you give your answer to the appropriate number of significant figures with the correct units, and you state whether the force experienced by an object is either attraction or repulsion. Now, because it's a negative value, it shows that our charges are attracting to each other. As I said before, do not forget to square your separation value. It's a common mistake in questions. And remember that both the free electron and the sphere are experiencing this charge. Now you can state if the force between the objects is attraction or repulsion by looking at the sign of the value. Now finally, you can investigate forces between the two charged metal spheres using Coulomb's law. Now the balls can be charged positively by touching each momentarily to the positive electrode of a high tension supply. Lowering one of the charged spheres down towards the other will produce a larger reading on the balance. Now this value on the balance can be used to determine the electric force exerted on either charged object. Now by measuring the separation between the charged objects, the total charge on the objects can then be calculated. However, when we're using this, the separation is measured from the centres of both objects. So to summarise what we've looked at in today's lesson, we know Coulomb's law, which is that the force between 2 point charges is equal to QQ over 4 pi epsilon 0 R squared. We've looked at the similarities and differences between the gravitational field of a point mass and the electrical field of a point charge, and then finally looked at the concept of electrical fields as being a number of forms of field giving rise to a force. So if we've been successful, and we've learnt in today's lesson, we can define what the force experienced on charged objects when near other charged objects is. We can note the similarities and differences between the gravitational field of a point mass and the electrical field of a point charge. And then finally, we can calculate and describe the electrical force experienced on charged objects in an electrical field. So thank you so much for watching this lesson, which is part of the Particles in Medical Physics module in OCR A-Level Physics in the topic of electrical fields and on the concept of Coulomb's law. Thank you so much and have a lovely day. Hello and welcome to the following video for OCR A-Level Physics, Module 6, Particles of Medical Physics, on the concept of electrical fields, looking at electrical field strength. So if we've been successful and we've learnt in today's lesson, we should be able to define and describe electrical field strength, describe how electrical field strength can differ in different electrical fields, and calculate electrical field strength. So in this lesson, we're going to be looking at the following parts of the OCR A-Level Physics. Now, electric field strength can be shown on the electrical field diagrams as the density of the electric field lines. We can define electrical field strength as the force per unit positive charge experienced at a position in the field. Now, there are two types of field. There are radial fields, where the electrical field strength changes at different places of it, whilst you've got uniform fields, where the electrical field strength is the same everywhere in the uniform field. Now, we know this is the case for radial fields, as the electrical field line density decreases with distance from the charged object, whilst we know this is the case for uniform fields, as the electrical field line density stays the same throughout the electrical field. Now, electrical field strength is a vector quantity. It points in the direction that a positive charge would move in. So electrical fields will point away from positive charges and towards negative charges. Now remember, all electrical field quantities are defined in terms of positive charges. So there's no fundamental reason why this is, it's just the standard notation of electrical fields. Now the units of electrical field strength are newtons per coulomb. Now there are three different equations to calculate electrical field strength in an electrical field. The first one is the general equation for every field based on its definition, where electrical field strength is the force divided by the charge, or E is equal to F over Q. So for example, what is the electrical field strength around a point charge if 3.2 times 10 to the minus 19 coulombs of charge experiences a force of 7.30 times 10 to the minus 15 newtons? Well, E is equal to F over Q, so it's 7.30 times 10 to the minus 15 over 3.2 times 10 to the minus 19, so it's 2.28 times 10 to the 4 newtons per coulomb. There's an equation when considering uniform fields only, that the electrical field between two parallel plates, for example a capacitor plate, is uniform, so a charge will experience the same force wherever it is placed between the plates. So the electrical field strength depends on two factors: the potential difference between the plates and the distance between them. So electrical field strength is potential difference divided by the distance between the plates, or E is equal to the change in potential over D. Now the units of electrical field strength in this instance are volts per meter. Now this tells us the units of newtons per coulomb and volts per meter are equivalent. However, volts per meter is only used in the context of uniform fields. Finally, there is an equation for radial fields. So if we consider two charged particles, each particle is producing a radial electrical field. We know the force on each particle is given by the equation F is equal to Q1 Q2 over 4 pi epsilon 0 r squared. Now we can define electrical field strength as the force per unit charge, so E is equal to F over Q1. So F therefore is equal to E Q1. Now we can substitute this into Coulomb's law. The charges of one of the objects will cancel through the Q1, which gives us the idea that E is equal to Q over 4 pi epsilon 0 r squared. So this gives us the equation for the radial field strength. Now note, only one charge is considered, as the electrical field strength is the force per unit charge caused by being in the electrical field of that charge. So in this equation, the Q term refers to the charge the object produced in the electrical field. So if we consider a radial electrical field of an object, from the equation we realise that the electrical field strength decreases with separation from the charge, making the field with the relationship E is proportional to 1 over r squared. So this is another case of the inverse square law. Now from the field line diagram, we realise that the electrical field strength decreases with separation from the charge, making the field, as the electrical field lines are spreading apart, the field line density is decreasing. However, if the charged object is not a point charge, then the field strength is not E is proportional to 1 over r squared at all points in the field. This relationship is only true from the surface of the charged objects. So to clarify, in this case, once we get past the surface of our charged object, the electrical field strength is equal to Q over 4 pi epsilon 0 r squared. So, to clarify, the electrical field strength is the force per unit positive charge experienced by a positive test charge placed at the point of that field, and it can be calculated with the following equation. The general equation is electrical field strength is equal to force over charge. The equation for the uniform field is electrical field strength is the potential difference divided by the distance between the plates. And the equation for the radial field is that electrical field strength is equal to 1 over 4 pi epsilon 0 times by the point charge divided by the distance from the charge squared. So we can see our equation for the general definition of the electrical field strength. The equation that shows the electrical field strength between two plates is dependent on the distance between the plates and the potential difference across the plates. And then finally, that the electrical field strength exerted by a charged object or a point charge is due to the charge of the object and the distance you are away from that object. So to clarify, our general equation is E is equal to F over Q. Our uniform equation is E is equal to delta V over D, and our radial field equation is E is equal to Q over 4 pi epsilon 0 r squared. So to summarise what we've learned in today's lesson, we've looked at the representation of electrical fields by electrical field lines, the concept of electrical field strength, E as a force per unit charge defined by E is equal to F over Q, and that the magnitude of E in a uniform field is given by E is equal to V over D. So if we've been successful and we've learnt in today's lesson, we should be able to define and describe electrical field strength, describe how electrical field strength can differ in different electrical fields, and finally calculate electrical field strength. So that brings an end to this lesson, which is part of Module 6 in OCR A-Level Physics, Particles and Medical Physics, in the topic of 6.2 electrical fields, and on our concept of electrical field strength. Thank you so much for listening, and have a lovely day. Hello and welcome to this lesson for OCR A-Level Physics on Module 6 Particles and Medical Physics in the topic of electrical fields, looking at the concept of the motion of charged particles in electrical fields. So if we've been successful and we've learned in today's lesson, we should be able to define and describe electrical fields, calculate the electrical field strength of both uniform and radial fields, and detail the trajectory of moving charged particles entering a uniform electrical field. So we're going to be looking at the following part of the OCR A-Level Physics specification, the motion of charged particles in a uniform electrical field. So a charged particle will interact with an electrical field when it is placed in that region. So consider a charged particle placed inside a uniform electrical field, as shown here. Now a uniform field will be produced between two parallel plates with a potential difference between them. Now we know this is a uniform field as the field lines are equally spaced out and there's the same field line density throughout. Now the field lines are pointing in the direction that a positive charge would move in at that point in the field. So this means that the lines will point towards the more negative of the two plates. Now the potential difference across the two plates which produces this field is 600 minus 200, which is 800 volts. Now if we place a charged particle in the field, it will experience a force due to being in that field. This is due to the definition of an electrical field. Now the magnitude of the force can be calculated using the electrical field strength equations. This force is also a resultant force, so will cause the particle to accelerate in a particular direction. So this is the mechanism which allows a particle accelerator to accelerate particles. Now the acceleration can be determined by the following equation. F equals ma, so a is equal to F over m. Now the acceleration experienced by a particle in an electrical field is therefore dependent on the charge, as F equals eq, and the mass of the particle. So the acceleration and the charge of the particle are directly proportional to each other. The acceleration and the mass of the particle are inversely proportional to each other. And the acceleration and the charge to mass ratio of the particle are directly proportional to each other. So if we consider a particle which is already moving in an electrical field, you can see in this image the charged particle has motion. Now the particle wishes to continue in its motion, it has inertia. However, if the electrical field is acting parallel to the charged particle, a resultant force will act on the object in the same direction as motion. So this will cause acceleration by changing speed. So when the electrical field is acting in the same direction as particle motion, it will cause the particle to accelerate by changing speed. Now remember, the field lines are the direction a positive charge would take. If a positive charge is moving along a field line parallel to the field line, it will speed up in the direction of the field line. whilst if it's a negative charge moving along a field line parallel to the field, it will speed up in the opposite direction to the field line. Now, if in this situation we consider this particle, which is already moving in the electrical field, once again the particle wishes to continue in its motion. It has inertia. However, if the electrical field is acting perpendicular to the charged particle, a resultant force will act on the object which is 90 degrees to its motion. So this will now cause acceleration by changing direction. So, when the electrical field is acting perpendicular to particle motion, it will cause the particle to accelerate by changing direction. This is because it is acting as a centripetal force. Now, once again, remember the field lines are the direction a positive charge would take. So if a positive charge is moving perpendicular to the field line, it will deflect in the direction of the field line. If a negative charge is moving perpendicular to the field line, it will deflect in the opposite direction to the field line. Remember, in all cases, the charged particle will not change speed but only change direction, as the force is acting perpendicular to the motion. So, just clarify, if we place a charged particle in the field, it will experience a force due to being in the field. This force is a resultant force on the object. So a positively charged particle will accelerate in the same direction of the field lines, since the field lines show the direction of positive charge movement, whilst a negatively charged particle will accelerate in the opposite direction, as the field lines show the direction of a positive charge movement. Now, if we place an uncharged particle in an electrical field, there will be no acceleration, as it feels no resultant force when in an electrical field from that electrical field. Now, once again, remember that the charged particle will only experience a force in the direction of the field lines. So this means it will experience no resultant force in the plane that is at 90 degrees. So in this example, the charged particle will only experience a resultant force in the vertical plane. So this means that the charged particles plot out a parabolic path in a uniform field, as only one plane of motion experiences a resultant force. Now, the parabolic path occurs as there's inertia in the horizontal direction and a resultant force in the vertical direction. This is the same principle as to why objects move in a circle with a centripetal force. So we know that this means charged particles will plot out a parabolic path, which means the particles will continue at the same speed in the plane at 90 degrees to the field. So if the motion of the charged particle is perpendicular to the electrical field, the electrical force accelerates the particle by deflection. So for a charged particle moving in an electrical field, the horizontal motion is that there is no acceleration, hence the horizontal velocity of the particle remains constant with the velocity v. And the time spent in the field is therefore given by the equation distance over velocity. Whilst in the vertical motion, the vertical acceleration is caused by an electrical force. A equals F over m, so it equals EQ over m. Our initial velocity is equal to u. Our final velocity is therefore v equals u plus at, which is 0 plus EQ over m times by L over v, which we can then simplify to equal EQL over mv. As we mentioned before, if the motion of the charged particle is parallel to the electrical field, the electrical force will accelerate the particle by changing speed. This will cause the particle to maintain the same direction of motion but change speed. So what we know is that a charged particle will be accelerated in the vertical plane but maintain a constant speed in the horizontal plane. Please do note this is only the case if the charged particle is already moving. If the particle was not moving when it entered the field, it would not carry out a parabolic path. Rather, it would accelerate directly up or directly down dependent on its charge. Inertia in one plane causes a parabolic path to be taken by the particle. Now we can work out the size of the deflection if the electrical field is perpendicular to motion in the path by comparing the charge to mass ratios of different charged particles entering the electrical field. The higher the charge to mass ratio of the particle, the greater the deflection of the charged particle in the electrical field. So if we consider a charged particle in a uniform electrical field, if the charged particle is stationary when it is in the uniform electrical field, it will accelerate in one direction given a straight line path. If the charged particle is moving perpendicularly to the uniform electrical field, it will accelerate in one direction and have an inertia in the other, giving it a parabolic path. We know that because the electrical field strength is constant and is equal to V over D. We know the electrical force on the charged particle is also constant and is equal to EQ, both because they're in a uniform electrical field. We also know our work done on the charged particle is VQ. Now horizontally, there is no acceleration. The horizontal velocity is constant and our time in the field is L over V. Whilst vertically, the vertical acceleration is A is equal to F over m or EQ over m, with the initial vertical velocity being equal to 0, and our final vertical velocity is V equals U plus AT, which simplifies to EQL over mv. So, if we consider a charged particle moving perpendicularly to a uniform electrical field, horizontally our acceleration is 0, vertically our acceleration is EQ over m, horizontally our initial velocity equals our final velocity, whilst vertically our initial velocity is 0, whilst our final velocity vertically is EQL over mv. Whilst our time in the field can be worked out via looking at the horizontal motion, which is equal to the length over the velocity of the object. Remember, horizontally there's no resultant force, whilst vertically the resultant force is the electrical force. Now this means vertically we have a constant acceleration in this plane, whilst horizontally we have inertia in that plane. So to summarise what we've looked at in today's lesson, we've looked at the motion of charged particles in a uniform electrical field. So if we've been successful and we've learnt in today's lesson, we should be able to define and describe electrical field strength, calculate the electrical field strength for both uniform and radial fields, and detail the trajectory of moving charged particles entering a uniform electrical field. Thank you so much for watching this lesson, which is part of OCR A-Level Physics, Module 6, Particles in Medical Physics, in our topic of electrical fields, and on the concept of the motion of charged particles in electrical fields. Thank you so much for watching, and have a lovely day. Hello and welcome to this lesson for OCR A-Level Physics, Module 6, Particles in Medical Physics, in the topic of electrical fields and looking at the concept of electrical potential. So if we've been successful and we've learnt in today's lesson, we should be able to define absolute electrical potential, detail the properties of electrical potential in an electrical field, and consider the concept of when work is done in an electrical field. Now, in the previous lessons, we have considered electrical fields. Now, the existence of an electrical field indicates that an object has charge. Now, through Coulomb's law, we've considered the force exerted on two charged objects due to their interacting electrical fields. Whilst the field strength details how much force per unit positive charge will be exerted on an object due to being placed there. Now, we can consider an object to also be a store of electrical potential energy when found inside an electrical field. So there must be another factor we can consider, the energy stored in an object due to being in an electrical field. So this concept is called the electrical potential. So the potential details the energy stored in one object per unit property of the field due to the object being in the field. And this is due to the field that is produced. Now, an example of this is the gravitational potential, which is the gravitational potential energy per unit mass experienced by an object inside a gravitational field. So if we consider an electrical field produced by a positive charge, remember the standard derivation of electrical fields favours the concept of using positive charge. So all electrical field notations use positive charge. Now, any other charged object placed inside the electrical field will become a store of electrical potential energy. Now, this electrical potential energy store is produced because of a resultant electrostatic force acting on the object due to being in the field. Now, this energy is due to the attraction or repulsion produced between the charges. Now, in general, work must be done to move a charged object towards another object that has the same charge. Their electrical potential energy increases as they move towards the object. So their electrical potential energy increases from 0 as they move towards the object from infinity, which we define as outside the field. So the electrical field of the stationary object causes a force of repulsion on the object which is moving. So this force must be overcome to move the objects closer to each other. So this gives us the concept of absolute electrical potential. This is the electrical potential energy stored per unit positive charge due to being placed at a point in the electrical field. Now we give this quantity the symbol V. Now we can set the absolute electrical potential to be zero at any place, however we choose to set it at infinity. Now we define infinity as any region outside of the electrical field. Now we set infinity to have zero absolute potential as the particle is outside of the field, so feels no force from the field, and it is no longer an electrical potential energy store. So we can summarize this with the following graph. So what we can say is that the electrical potential is equal to zero at infinity, very, very far away. Now the test charge would normally move towards a negative charge due to electrostatic attraction. So therefore this would decrease our absolute electrical potential. But work needs to be done to pull the positive test charge away from the negative charge, so it would increase the electrical potential. So as we can say, the electrical potential, V, decreases in the direction the test charge would naturally move in due to attraction or repulsion. Now we can calculate the absolute electrical potential with the following equation. That absolute electrical potential is equal to the electrical potential energy stored divided by charge, or V is equal to E over Q. Now this equation comes from the definition of absolute electrical potential, and this gives the units of our absolute electrical potential to be joules per coulomb. Now this is also the same as the volt, so 1 volt is equal to 1 joule per coulomb. Now this makes sense as the definition of potential difference from the module electricity is the work done per unit charge, and this is very similar to the definition of absolute electrical potential. Now the unit of potential difference is also the volt. So therefore, if the charge in the field is positive, this would make the electrical potential also be positive, as there is repulsion. So it means that if the charge starts off close to the charge making the field and moves away, the potential tends to zero as the charge object moves to infinity. Whilst if the charge in the field is negative, then the electrical potential is negative as it is attracting. Now if the charge starts off far away from the charge making the field and moves closer, this means the potential tends to infinity as the charge object tends to zero. So these definitions lead to the following graphs. So this is a graph which shows how the electrical potential of an object changes with the distance from the charged object producing the electrical field. So we can consider this part of the graph to be when the object in the field is experiencing a repulsive force, and this part of the graph shows when the object in the field is experiencing an attractive force. So with repulsion it starts off as positive, and as the distance increases it tends to zero but always stays as a positive value. So as a reminder, this is for positive charges. Whilst on the other side, we start with its attraction, it starts off as negative, the distance increases and it tends to zero, but it always stays negative. And this is for our negative charges. So we can summarize it again with the following graph. The values for V are all negative for a negative charge. The values for V are all positive for a positive charge. As R increases, V against R follows a 1 over R relation for a positive charge and a minus 1 over R relation for a negative charge. The gradient of the graph at any particular point is the value of E, the electrical field strength at that point, and our graph will show a shallow increase or decrease as R increases. Now we can also calculate the absolute electrical potential for a radial field with the following equation. V is equal to Q over 4 pi epsilon 0 R. But this equation is only applicable to radial fields. Now remember that the field strength and force are related to the separation from the charge by the term 1 over r squared, but energy and potential are related to the separation by the term 1 over r. Now we can derive this equation as we know the work done per charge is equal to the force per charge times by the distance. Therefore multiplying the electrical field strength by the distance gives the electrical potential. So if we say work done per charge equals force per charge times by distance, we can say V is equal to E times by D, where E is equal to Q over 4 pi epsilon 0 r squared times by r, so it equals to Q over 4 pi epsilon squared r. So therefore we can say multiplying the electrical field strength by the distance gives our electrical potential. Now, we can also say that because the field strength and force are related by the separation of the term by the 1 over r squared, this is an inverse square relationship. Whilst because the energy and potential are related to the separation by the term 1 over r, this is an inverse proportional relationship. Now we can also use the principle of dividing the electrical field strength by the distance to find the electrical potential for uniform fields. However, this gives us the startling conclusion that if E equals V times by D, and therefore V equals E times by D, we can therefore say it equals V over D times by D, so we're saying V equals V. Now we can also link this back to our absolute electrical potential, which is electrical potential energy over charge, as this equation can be used for any electrical field. So this tells us we can interchange these equations if the field produced is radial, which is produced by a charged sphere. Now this can be useful when deriving values in questions, but please be aware that the electrical potential is a vector, whilst the electrical potential energy is a scalar. Now, electrical potential is defined as a positive when showing repulsion and a negative when showing attraction. So the vector quantity in electrical potential comes from the charge aspect of the equation, whilst the electrical potential energy is a scalar term as it's stored in the object. There's no direction to the energy stored in an object. Now, as electrical field strength and electrical potential are vectors, we can use this to determine resultant values when there are multiple charges present. This can be easily determined for a point between two charges, because if you want to work out the resultant electrical field strength at a point x between the two objects, you must carry out the following. Work out the electrical field strength at point x from charge A. Work out the electrical field strength at point x from charge B. Sum the two values, but beware it's likely that they're acting in opposite directions, so this will in fact be a subtraction. Now again, if you wanted to work out the resultant electrical potential at point x between the two objects, you carry out the following. Work out the electrical potential at point x from charge A. Work out the electrical potential at point x from charge B. Sum the two values, but once again, beware it's likely they'll be acting in opposite directions, so they'll be subtracted. So for example, in this following scenario, work out the electrical field strength at point x. Well, from charge A, E is equal to Q over 4 pi epsilon 0 r squared, so it's 4 times 10 to the minus 9 over 4 pi epsilon 0 times by 0.45 squared, which is 177.6 newtons per coulomb to the right. We then work out the electrical field strength from charge B, 1 times 10 to the minus 9 over 4 pi epsilon 0 times by 0.30 squared, which is 99.9 newtons per coulomb to the left. As one is acting to the right and one to the left, we can then sum them, which is actually a subtraction, so it's 17.7 newtons per coulomb to the right. And we can also, for the same situation, work out the electrical potential at point x. So you can work it out from charge A, where V equals Q over 4 pi epsilon 0 r, so 4 times 10 to the minus 9 over 4 pi epsilon 0 times by 0.45, which is 79.9 volts. We can then work out the potential from the electrical potential from charge B. So it's minus 1 times 10 to the minus 9 over 4 pi epsilon 0 times by 0.30, which is minus 20 volts. The resultant, again, is the two summed, which is the subtraction, so it's plus 59.9 volts. Now again, we could work it out if there are two positive charges. So again, you would work out your electrical potential from charge A, which is 79.9 volts, and this time work out the electrical potential from charge B. But now it's positive 20 because it's a positive charge, so therefore all positive charges produce positive potentials. So you sum them, which is now an addition, so it's plus 99.9 volts. Now we can also determine the actual electrical field strength or electrical potential at a point at right angles between two charges. So if you wanted to work out the resultant electrical field strength or electrical potential at point x between two objects, you must carry out the following. Work out the electrical field strength or potential at point x from charge A. Work out the electrical field strength or electrical potential at point x from charge B. Sum the two values by using the Pythagorean theorem. So for example, in this situation, how do you work out the electrical field strength at point x? Well, you work out the value of the electrical field strength due to charge A. So E equals Q over 4 pi epsilon 0 r squared. So you work that all through to be 899 newtons per coulomb upwards. Whilst from charge B, we can see that E is equal to Q over 4 pi epsilon 0 r squared, so you work it out to be 99 newtons per coulomb to the left. Now our resultant is due to the Pythagorean theorem, the resultant is equal to 899 squared plus 99 squared, all square rooted, is 904 newtons per coulomb. Whilst our resultant angle is tan is equal to opposite over adjacent, so it equals 84 degrees. So to summarise what we've learnt in today's lesson, we can understand the definition of absolute electrical potential, including the zero value at infinity, and an understanding of electrical potential difference. We also can understand that the work done in moving charge Q is given by the equation that the work done is equal to Q times by delta V. So, if we've been successful and we've learnt in today's lesson, we can define absolute electrical potential, detail the properties of electrical potential in an electrical field, and start to consider the concept of when work is done in an electrical field. So thank you so much for watching this video for OCR A-Level Physics in Module 6 Particles and Medical Physics in the topic of electrical fields, looking at the concept of electrical potential. Thank you so much and have a lovely day. Hello and welcome to the following video for OCR A-Level Physics on Module 6 Particles and Medical Physics in the topic of electrical fields, looking at the concept of electrical potential energy. So if we've been successful and we've learnt in today's lesson, we should be able to define absolute electrical potential, detail how to calculate the electrical potential energy stored or transferred in a situation, and then finally consider the concept of when work is done in an electrical field. So in our previous lesson, we defined the concept of absolute electrical potential, that any charged object inside an electrical field will have an absolute electrical potential. So we said that the absolute electrical potential is the electrical potential energy stored in the object per unit positive charge due to being located at that point in the field. So any charged object in an electrical field will therefore become a store of electrical potential energy. Now electrical potential energy is considered a scalar quantity, as the electrical potential energy is stored in the object. Now this is considered an absolute quantity, as it's not dependent on any other factor except our electrical field. So our electrical potential is the work done per unit positive charge to move a charged object from infinity to a point in the electrical field. Now at infinity we have defined the electrical potential to be zero. This is because the object is not in the electrical field. Now inside the electrical field, the electrical potential is non-zero, as it has become an electrical potential energy store due to being in the field. Now it's important to note that this value for electrical potential is either going to be a positive or a negative depending on the attraction or repulsion. So to clarify, absolute electrical potential is the electrical potential energy stored per unit positive charge due to a charged object being placed in the field, whilst electrical potential is the work done per unit positive charge in moving a charged object into the electrical field from infinity. Now electrical potential and absolute electrical potential will always have the same magnitude. Now the direction or sign might be different, as the electrical potential considers attraction and repulsion. And it also leads to a real fundamental concept in physics, that moving an object into different values of potential means work needs to be carried out. So if a charged object moves between areas of different potential, work must be done into or out of the object. So this direction of work is given either by the attractive or repulsive nature of the force. So if we consider the following electrical field, the dashed lines in the electrical field diagrams represent areas of different potentials found in the electrical field. Now charged objects can move between different areas of electrical potential, but this requires work to be done. So we say that the charged object has moved due to potential difference. Now this is the process behind how all currents are produced in electrical circuits. A potential difference causes a current, a flow of charged particles. Now the potential difference, or delta V, is calculated by working out the difference between the potential areas the charged object has moved between. So in this example we can say delta V is equal to 300 minus 180, which is 120 volts. So a charged object in an area of potential difference will accelerate. So we know that the potential difference is the work done per unit charge needed to move a charged object. Now this is because the electrical potential is the energy at each level per unit positive charge. So this gives us our following equation. Delta V is equal to delta W over Q, which can be rearranged to say delta W equals Q delta V. So this equation tells you that the work done needed to move a charged object between 2 points of potential difference in an electrical field. Now the Q term in this equation refers to the charge of the object moving, not the charge of the object producing the field. So that's important because the equation refers to the work done on the object in the field, so the charge must be that of the object moving. Now it's important to note that the previous equations, such as electrical field strength and potential, work out the properties of the field itself, so need the charge of the object producing the field. Now this equation also tells you that the work done needed to move a charged object is directly proportional to the potential difference if the charge remains the same. It also indicates to us that it is also directly proportional to the charge of the object if the potential difference remains the same. So let's have a look at a worked example. The potentials at point R and S are due to the plus 7 nanocoulomb charge at 675 volts and 850 volts respectively. Calculate how much work is done when a plus 3 nanocoulomb charge is moved from R to S. So the first step is to write down your known quantities, that the PD at R is 675 volts, the PD at S is 850 volts, so the charge Q is equal to plus 3 times 10 to the minus 9 coulombs. We know our equation is the work done times by the charge equals the work done the work done is equal to the charge times by the potential difference. So therefore it is 3 times 10 to the minus 9 times by 850 minus 675. So it's 5.3 times 10 to the minus 7 joules. Now as we know that the absolute electrical potential is equal to the electrical potential energy over the charge, we can use this to determine an equation to calculate an equation for electrical potential energy. So we know electrical potential energy is equal to QQ over 4 pi epsilon 0 R, where big Q is the charge of the object generating the electrical field, and small q is the charge of the object in the electrical field. Now the electrical potential energy is the stored energy a charge has because of its position in an electrical field. It depends on both the electrical potential at that point and the magnitude and sign of the charge. Now changing the electrical potential, a potential difference, causes the value of the electrical potential energy stored to be changed. This is work done. Now as a charge moves in an electrical field, any loss in electrical potential energy equals a gain in kinetic energy if no other forces act. So if you move a charge against the electrical field, you will increase its electrical potential energy. If you let the field move the charge with the field, the charge loses electrical potential energy, which can convert into kinetic energy, similar to a ball rolling downhill. Now a positive potential electrical potential energy means that the energy is stored in a repulsive configuration, like two positive charges close together. A negative potential electrical energy means that the energy is stored in an attractive configuration, like opposite charges close together. So let's just recap our key information. Electrical potential is equal to Q over 4 pi epsilon 0 R, and it's the work done per unit positive charge from infinity, whilst electrical potential energy is equal to QQ over 4 pi epsilon 0 R, or QV, which is the total work done bringing a charge Q from infinity. Now the force F between two positive particles or spheres of charge Q and Q varies with their separation as shown in the diagram below. This is given by the Coulomb's law relationship of F is proportional to 1 over R squared, which is shown in this diagram. Now the area under a force distance graph is equal to work done. Now the total work done to bring the particles from infinity to a separation R is the total area under the graph, which is shown by our shaded region. Now the magnitude of this value of E represents the external energy required to completely separate the charged particles to infinity. Now the area under the graph can be estimated by counting squares if it is plotted on squared paper, or by splitting it into trapeziums and summing the area of each trapezium. Now if we consider the following electrical field, in this diagram the dashed line shows the plane in the field where the electrical potential is the same. Now as the potential along the line is always the same or equal, we call this a line of equipotential. Now, work is needed to be done to move a charged object between planes of different potential, but there is no change in potential along a line of equipotential. So this means charged objects can move along lines of equipotential without work being done. So here, in this different situation, because the charged object will travel along the equipotential line or surface, no energy will be being transferred. Now, in radial fields, the surfaces of equipotentials are spherical spheres. The lines of equipotential are always represented by dashed lines, and the lines of equipotential are found at 90 degrees or perpendicular to the field lines of the electrical field. Now, you will be expected to deduce lines of equipotential from electrical field diagrams. Now, we can show this also in a uniform field as well. Still, the lines of equipotential are found to be at 90 degrees to the field lines of the electric field. Now again, you will be expected to deduce your lines of equipotential from electrical field line diagrams. So let's summarise what we've looked at in today's lesson. We should have an understanding of absolute electrical potential, including the zero value at infinity, and of electrical potential difference. Understand that the work done in moving a charge q is given by delta W equals Q delta V. The understanding of equipotential surfaces, and that no work can be done by a moving charge along an equipotential surface, and that the magnitude of V in a radial field is equal to 1 over 4 pi epsilon 0 Q over R. So if we've been successful and we've learned in today's lesson, we should be able to define absolute electrical potential, detail how to calculate the electrical potential energy stored or transferred in a situation, and consider the concept of work being done in an electrical field. So thank you so much for watching this video for OCR A-Level Physics in Module 6 Particles and Medical Physics in the topic of electrical fields, looking at our concept of electrical potential energy. Thank you so much for listening and have a lovely day. Hello and welcome to this lesson for Module 6 of Particle and Medical Physics for OCR A-Level Physics, looking at the concept of electrical work done in the topic of electrical fields. So if we've been successful and we've learnt in today's lesson, we should be able to sketch and interpret graphs of V against R for positive and negative point charges, describe how the potential difference can be deduced from a graph, and consider how the potential gradient of a field is linked to the electrical field strength. Now in our previous lesson we've considered the following planes of equipotential in an electrical field. Now an equipotential line is a line or surface along which the electrical potential is the same, much like a contour line for a height on a map. Now equipotential lines are very useful when interpreting the electrical field strength near charged conductors. However, we can also consider the planes of equipotential to be like blocks. So here is another way of visualizing electrical potential. Now this is a representation of how the electrical potential varies in an electrical field. So we can consider a representation of how the energy stored per coulomb varies in an electric field. So this produces what we call a potential gradient in the electrical field. Now our potential gradient can be thought of as the change in electrical potential with respect to distance. So we can think that the closer the planes of equipotential in the field, the greater the potential gradient in the electrical field. Now charged objects can travel down the potential gradient, but work must be done to achieve this. So here the electrical field is doing the work to move the charge. So we can say the electrical field is attracting the charge. So we know the electrical field is doing the work moving the charge, so we consider the work done to be negative. So when there's attraction between the charges, we say our work done is negative. Now electrical fields can also produce no potential gradient as well. So if a charged object does move along a potential gradient with nothing, then no work must be done. This is a line or surface of equipotential. Now, going down a potential gradient, work is done out of the system, while going up the potential gradient, work is done into the system. So in this case, we have a positive value for work done. This is when there's repulsion between the charges and we have a positive work. Now the steeper the potential gradient, the more work that must be done to that charged object. So a steep gradient means that a lot of work must be put into the system to move the charged object up the gradient. So it means that a steep gradient can have a lot of work being released from the system to move a charged object down the gradient. So The potential gradient at any position in an electrical field is the change of potential per unit change of distance in a given direction. If the field is non-uniform, the potential gradient varies according to the position and direction. The closer the equipotentials are, the greater the potential gradient is at right angles to the equipotentials. If the field is uniform, the lines of equipotential are equally spaced out, so our potential gradient is constant. Now we can graph this concept of potential gradient. So the gradient of this graph of V against R is called the potential gradient. So as we said before, the change of potential per unit change of distance in a given direction. So the closer the equipotentials are, the greater the potential gradient. So this means the graph will be the electrical potential against the distance from the charged object producing the electrical field. So the steeper the line, the greater the potential gradient, the more work that must be done into or out of the system. So our gradient is the change in y over the change in x, or delta V over r. Now we can place this equation for potential into the following equation. We know the gradient is delta V over r, where V is q over 4 pi epsilon 0 r. So we divide that by r. So therefore this tells us that gradient equals q over 4 pi epsilon 0 r squared. So this means that the potential gradient is the same quantity as the electrical field strength. So potential gradient is the electrical field strength. The gradient of a V against R graph is the electrical field strength. So we can consider the potential gradient as the magnitude of the electrical field strength. Now this is because it doesn't show the direction of the field. So as we said before, we can graph the potential gradient for a uniform field. The gradient of this graph is our potential gradient. Here, the equipotentials are equally spaced out, giving a straight line. So the electrical field strength doesn't change, as such the gradient doesn't change. So as mentioned, the electrical field strength is equal to the potential gradient produced. So here, our equipotentials are equally spaced out, the electrical field strength doesn't change, our gradient does not change. Because the electrical field strength is equal to the potential gradient. So in a uniform field, the electrical field strength is constant, so the gradient is constant. You get a straight line. Now here we can see that the electrical potentials can change how spaced out they are as the field lines spread out. So our electrical field strength does change, indicating that gradient will be changed because the electrical field strength is equal to that potential gradient. So in a radial field, our electrical field strength is decreasing with respect to distance. So the gradient is decreasing, you get a curved line. So here is a comparison between the two graphs illustrating the potential gradients produced. You can quite clearly see the link between electrical field strength and the gradient of the line. Here, the gradient follows the trend for an inverse square law because E is equal to q over 4 pi epsilon 0 r squared. Here, our gradient is constant for a uniform field as the electrical field strength doesn't change. Now from the previous graph we can also derive another key idea. Now do note that the gradient of the tangent to the graph will be the gradient or the electrical field strength of the field. So here V is changing with R for a positive charge as we define the field in terms of positive charges. V is initially positive and tends to 0 as R moves to infinity. Whilst here, V is changing with R for a negative charge. Again, now we're defining it in terms of positive charges. We must have a negative value for a negative charge. V is initially negative and tends to 0 as R moves to infinity. So if we consider the gradient of our graph here, gradient is delta V over R, which is the electrical field strength. We can rearrange this equation to make delta V the subject. So delta V is equal to E times by R. So this shows us that the area under the line of an E against R graph gives you the potential difference a charged object experiences, because the area is equal to the y-axis times by the x-axis. So if you're asked to estimate the potential difference on delta V from an E against R graph, you will have to work out the area under the graph by counting the number of squares or by splitting the areas up into trapeziums. This concept allows you to derive the electrical potential equation stated earlier in the course. It's the graphical derivation for the equation of electrical potential. We know E is equal to V over R, so V is equal to ER, so we know V is equal to Q over 4 pi epsilon 0 R squared times by R, so at that point we can say V is equal to Q over 4 pi epsilon 0 R. So you must be aware of the electrical properties from two electrical field graphs. So in our electrical potential against different distance graph, V against R, we can say our gradient is the electrical field strength. Whilst the electrical field strength against distance graph, ER, the area is the potential difference. So this can be summarized in the following table, that we can see that the force is equal to Q1 Q2 over 4 pi epsilon 0 r squared. The potential energy, which is the area under an F against R graph, is equal to Q1 Q2 over 4 pi epsilon 0 r. The field strength, which is also the potential gradient, or the gradient of a VR graph, is equal to Q over 4 pi epsilon 0 r squared. Whilst finally our potential, which is Q over 4 pi epsilon 0 r, is our area under an ER graph. So thank you so much for watching this lesson on electrical work done, which is part of the electrical fields topic in Module 6 of OCR A-Level Physics, which is particles in medical physics. Thank you so much for listening to this video, and as always, have a lovely day.